Okay, so let me strike forth from where I was yesterday. Actually, we had this. We had a map into here. So an element sigma from GQ mapped to the chi of sigma cycloatomic character and F sigma. Now, since Makoto talked so much about F sigma this morning, I'm not going to recall it because I think that you've all heard about it for a couple of hours. So what I want to say is the goal, okay, Makoto's goal and my goal are the same goal, and they understand this element. But his attack that he showed this morning was to look at this in a quotient of F2 prime, which is simpler. He quotiented out by some fairly large subgroup, and then he was able to compute the image explicitly in the quotient group, so that was nice. The way I'm going to look at this element is I'm not going to quotient by anything. I'm going to try to find, so one strategy thus is compute, strategy one, compute it in quotients of F2 hat, and strategy 2, okay, so here's the deal. This is a strategy which can be followed and accomplished, but at the end of it, what you know is you still don't have sigma because you know it in quotients, and you don't know it itself. Whereas my strategy, you aim to know the whole of F sigma, except that my strategy will fail because we don't know how to do it yet. Okay. I really have to learn to do this. Strategy 2 is find necessary and sufficient conditions on an F in F2 hat prime for it to come from GQ. Okay? So what we can do is find quite a number of very pretty necessary conditions. And that's what I'm going to do. What we cannot do is to say anything about the sufficiency of these conditions. So that remains still a totally open question. So the way that I'm going to introduce finding some necessary conditions on F is following Grothendieck's plan that I kind of sketched out in the previous lecture, which is GQ acts on fundamental groups, and running using the structure of those fundamental groups to see what we can say about the Fs. And the first fundamental group we looked at was the fundamental group of P1 minus 3 points, and that doesn't have any structure in the sense that it's just free. But that was already the group that allowed us to say that this F sigma even existed. So that was step 1. So we've done step 1. Now I'm going to look at more fundamental groups, and the question is, which fundamental groups am I going to look at, and why those? Okay, and the answer is we will consider fundamental groups of all moduli spaces of curves. So I'm going to have to say what these are and describe their fundamental groups. I'm going to have to spend some time on that. So the point is, a moduli space of curves is a space parametrizing many, many curves. So the moduli space is indexed by G and N. G is a genus, and N is some fixed integer, some fixed positive integer. And this is the name of the moduli space. Each point of this space is an isomorphism class of Riemann surfaces. Of genus G with n points somehow distinguished, and n, so x1, xn distinguished points for whatever n is. Okay, so now you agree with me, having written this, that this here is a well-defined set. But really, it's much more than that. It actually forms a space. It itself forms an algebraic variety defined over Q, which is a big theorem. It has lots of beautiful properties. It's a big theorem, which certainly is beyond the scope of what I'm going to do. But what I can do is I can show you what they're like for G equals 0, because in that case, they're actually quite simple, and you'll immediately see why this is true. So special but very important case, G equals 0. So when are we talking about G equals 0? We're talking about genus 0 curves. That is, we're talking about the Riemann sphere. That's it. So if I want to give you a curve of type 0n, it means that I just give you n points on the sphere. That's it. To give you a curve means that I tell you who my n points in P1 are. But I said that these were isomorphism classes, not just curves themselves, so I have to know when two tuples are isomorphic. When I write a tuple of points like this, I'm really thinking a curve minus these points. I'm thinking P1 minus these points, okay? I'm really going to mix up the notation, a tuple of points and the curve P1 minus these points, or with these marked points, and a point of this. So all I have to do is tell you when they are isomorphic. So that's easy because the automorphisms of P1 are just PSL2 of C. So these two are isomorphic if and only if there exists a gamma, which I represent by a matrix, but it's in PSL2 of C, such that gamma of xi, which is just axi plus b over cxi plus d, is yi for each of the i's. So if I have two tuples related this way, that's the same point in moduli space. That's isomorphic. So that's the same point in moduli space. So this is nice because what it means is easy exercise, given such a tuple, there exists a unique gamma in PSL2 of C such that PSL2 of Z has a property which is called being triply transitive. It means that I could take any 3 points and send them where I want. And that's obvious because there are 3 degrees of liberty here. It looks like 4, but it's not really 4 because what I'm doing is taking the quotient. There are 3 degrees of liberty. So I can always map, say, this is just a choice of normalization. I'm going to use this one. The first 3 to 0, 1, and infinity. And then let the remaining n minus 3 go where they may. So the conclusion is there exists a unique representative in each isomorphism class of the form 0, 1, infinity, y1, yn minus 3. So this is really nice because now what I've done is I've literally parametrized the genus 0 moduli spaces. So what are they? Well, these can all vary freely, except that they have to all be distinct. Oh, my definition is distinct points, n distinct. They're really not allowed to meet. So these points all have to be distinct. So what that means is it's just each of the yi's has to be different from 0, 1, and infinity. So each yi is in here, and I have n minus 3 of them. But I also have to take off what's called the fat diagonal, which is the bunch of lines where all of them don't meet each other. So it's the union of the yi equals yj's. Okay, and that's it. That's the moduli space in genus 0. So now that I've written that, of course, there it is. It's not exactly a variety. It's a quasi-variety. It's got sub-varieties removed, but it's still a perfectly simple space that we can really master, understand, whose fundamental group we can and will compute, and so on. So what about M04? Well, we look at that and we find this delightful fact. Okay, so this gives a whole new light, really sheds a whole new light on why it is that we keep looking at P1 minus 3 points, and even more than that. What is a right and interesting way to generalize P1 minus 3 points to a further bunch of spaces? So what Grothendieck said was, he examined this thing at length, he did the descent enfant theory that I told you about yesterday, and then he said, now that we've looked at the GQ action on this and we found that an F sigma exists, and this is already very exciting because it's so much more easy to look in F2 than it is to just look in GQ, now we should use all the pi1s of all the moduli spaces and natural maps between them to find out more about these F sigmas, to get a bunch of properties of these X sigmas. And he suggests and hints, I won't say he conjectures because that's not true, and anyway, in the way I'm talking about an unpublished text by Grothendieck here, which is written in a very visionary manner. So I'm not even going to say he goes so far as to conjecture. But he certainly says there should be good reasons to think that all the properties given on the F sigmas by these fundamental groups could be all properties needed to pick out GQ. Now, this is not known to be either true or false. We just don't know. It's really, really mysterious. In fact, it's not easy to even explain why he considers that the moduli spaces, not the genus 0 ones, but all of the moduli spaces, should be somehow enough. Let's see. What if we don't take the moduli spaces? What if we take all fundamental groups of all varieties? Divide over Q, of course. What if we take everything? And we look at the conditions every time when we know that F sigma is going to be an automorphism of those pi ones, like we saw an exact sequence explaining that, and Makoto talked about it again today. So we know it acts, so that gives some properties on it by the generators and relations of that pi one. So what if we use everything that you get from every pi one of everything? Then, do you get GQ? Okay? You take F a priori, you just take it in F2 hat. What I'm talking about here is necessary and sufficient conditions. So the answer to that question is you get GQ. So let me go all the way down here. So idea for the necessary and sufficient conditions. Take all conditions on an F in F2 hat. I'm ignoring the chi of sigma. I'm ignoring the lambda part right now, but of course one should do it in full detail with that as well. But this is really the important part of that. Coming from, it's acting on all pi ones of all Q varieties. And let me say, respecting all the natural maps between these pi ones coming from maps between the Q varieties. So acting on really the category of fundamental groups, including its natural morphisms. Then, F indeed comes from GQ. Now, I think I'm not sure if you recognize what I'm saying or not, but.
No, actually, that was my question.
Who?
Sorry.
Oh.
Could you explain a little bit clearly what that means?
Well, actually, here's a horrible moment where I have to confess I wasn't in Florian's talk. But did he talk about this? Florian? Oh, there you are. Did you talk about? You didn't talk about this. Are you going to talk about this? Okay. Okay, well, at the risk of then not doing other important things, I will spend a minute on this because it's really, really a very beautiful result due to no other than Florian Popp. So, answering a question posed by Oda and Matsumoto, so it's very relevant to this winter school. So I'm going to spend a minute talking about it. Here is a category. I'm going to give you a category, C. I'm going to give you two categories. The first one is going to be objects, some Q varieties. I'm not going to tell you which ones because I just want to take some. It's going to vary. In a minute, I'll say what happens when we take all Q varieties, and then we'll take only some Q varieties, whatever. But just take some Q varieties. Maps, morphisms, all Q morphisms between them. Okay, so there's my category. And now I'm going to associate to this category an associated category, C sub pi, objects, pi 1 of the above, morphisms, so all Q morphisms phi, phi lower star induced on the pi ones by the morphisms of there. Okay, now what do I mean by the automorphism group of C pi? So that's easy. Let me define. Aut C sub pi is going to be tuples of phi x indexed over the x's in C each No, why? Huh? Okay, well, no, well, it's nice to choose a compatible set of base points. But okay. Up to inners. Okay, then I get to make my diagrams commute up to inners, which isn't actually as good as it could be, but okay, I don't want to spend too much time on this, so let me do it up to inners. So, okay, because of that, I'm going to take everything in out pi 1. But these phi x's have to respect, within one tuple, every time I have an xy with a phi that was in the category, and here's my, every time I have an xy, I have an associated phi star, which we'll now consider as an outer, that is everything's up to inners. And here I have the phi of x and the phi of y coming from my same tuple, and this all has to commute up to inners. One can actually do a bit better than this, but okay, let's do it this way. So what is the odd of the category? It's compatible sets of oughts of everybody in it, compatible with all the maps. That's what it is. So here is the Popp's unpublished theorem answering a question of Oda and Matsumoto. Better call this out then, huh? C pi equals GQ if C is everyone, all Q varieties. Okay? And in fact, I think he got lots and lots of improvements on this where you don't have to take all Q varieties. You can take much, much less. You can take P2 minus hyperplanes. Okay, but you still have to take a very large number. But let me just put here if C equals all Q varieties, just to stay simple, even though the result certainly can be improved. Okay? So this gives a really much better idea of why we would have any hope by taking less Q varieties and still getting GQ. But what's the point of taking less Q varieties? Why would we bother since now we have GQ? Well, that's because you can't compute anything here. You can't compute one element which is an odd. There are too many pi 1s. You can't compute all the properties of F. There's there's an infinite infinity of these. So we didn't get that much in the sense that we didn't get any properties on F. I mean, we can't say these are the properties on F that make us have an odd of C pi. But we did get something which says, so trying to make a smaller category and make these still work is a good strategy. So the point is, what Grothendieck was saying was do the same thing, but now take the category to be all moduli spaces. But now we gain a wonderful thing, which is going to be the point of my next two lectures, is we can totally calculate the out. But we lose a wonderful thing because we don't know this is true anymore. We only have the GQ is in the out that we're going to get, but we don't have that it's equal. That has to remain conjectural. So every time you gain something, you lose something in this game. It's really annoying. But these are all outs now. It's okay? I can do this? Okay. All right. So this helps me state my goal. So my goal is exactly to calculate ought of C pi, where the C is the category of moduli spaces. I'm going to give you the answer before I do it. I'm actually going to tell you who it is, and then we'll see everything we can prove about it. So now that I'm completely off schedule, I have not even started yet. Oops. Okay, now we have the moduli spaces. Let me talk to you about the pi 1s of these moduli spaces. I'm really sorry for never having any base points. I know algebraic geometers hate this, but let me do it kind of topologically. So an element, as we saw, is for all practical purposes a Riemann surface. Okay, it's up to isomorphism, but let's say it's a Riemann surface. What is a Riemann surface? A Riemann surface is a topological surface of the right type, and then it has these n points on it, but topologically for the moment, and then this has to be equipped with an analytic structure. So I'm going to call this sigma Gn. This is a topological surface, an analytic structure. That's what a Riemann surface is. And giving an analytic structure, so giving a Riemann surface, gives me a point. And varying the analytic structure makes me vary inside this space. So if I parameterize a one-parameter variation, continuous variation of the analytic structure, I am getting a path in here. I start from some point, and as the analytic structure varies, I keep getting different Riemann surfaces and moving around the moduli space. And if it's going to be a loop, I have to get back where I was before. So in fact, a diffeomorphism, which is nothing but a way of continuously varying this until I come back to the place where I was before, yields a path on MGN. Any continuous variation of the structure yields a path. A diffeomorphism yields a loop. So when I'm doing what I talk diffeomorphism, I'm constructing the pi one. In a minute, I'm going to make this even clearer by describing a generating set of diffeomorphisms where you can really see what paths they give. Okay, but I said loop. I didn't say loop up to homotopy now. If I want the pi one, I have to talk up to homotopy. So what do so I have a map here. I've just created a map. Let's say orientation preserving diffeomorphisms. Maps to pi 1 MGN. I just explained that. But now I have to explain who the kernel is. The kernel is, just to say that the loop is defined up to homotopy turns out to be the same as to say that the diffeomorphism is defined up to isotopy, which is quite a theorem, actually. It's not a triviality. It has to be proved. But I just mod out by the diffeomorphisms which are isotopic or even homotopic, because you're not homotopic to the identity. Okay, so really the continuous, the connected component, the identity. And what I have now is an isomorphism. This is a way of interpreting the pi 1 of MGN at any given base point. I fix a base point, and then every time I pick that Riemann surface and I do a topological diffeomorphism that gets back to where it was, what that's doing is describing a loop on my space. So generating set of diffeomorphisms is a very important, a beautiful generating set. It's really useful, is the Dane twists. And they're just so nice and easy to describe. I'm going to tell you who they are. Along simple closed loops. So I take my sigma and I pick a simple closed loop on it, like this. And what I do is I cut out a neighborhood of this loop. So a neighborhood of this loop is just like a little cylinder. So I'm going to cut my surface into 3 pieces. The middle one which will just be a neighborhood of the loop. So just a cylinder. Okay? And now the diffeomorphism is going to affect only this. It's going to be the identity on that and that, my diffeomorphism. So I take this central thing and I fix this boundary here. And I take that boundary and I make a whole 2 pi twist. So I twist the whole thing around by 2 pi. And then I glue it back together. So just on the cylinder alone, it's a bit hard to draw a twist, okay, but you see what I mean. I grab this and keep it fixed, and I take that and I twist it around once completely. So I've got the identity on both boundaries now, so I can just re-glue. After having done that, re-glue. Okay, so I've got a diffeomorphism, and that's the Dane twist along a simple closed loop. But if I take all possible simple closed loops on my surface, I've got a generating set for the group of diffeomorphisms, and therefore for the pi 1 of MGN. Now, let's look in genus 0. in GINA 0, so first of all, M04, so I've got sigma 04 is a sphere with 4 marked points. So how many simple closed loops can I have up to diffeomorphism on this, basically? Because all that matters is which points are surrounded by the loop. So basically I have 3 loops. I have lots more loops, of course, but they're up to diffeomorphism, they're always equal to one of these 3. So I can take these 3 as a generating set. So these 3 loops generate, let me call them x, y, and z. And the product of the 3 is equal to 1. And in fact, the group pi1 M04, which I also call gamma 04, is equal to this xyz mod xy equals 1, which is of course equal to f2, which is of course equal to pi1 of p1 minus 3 points. So it's just another way of saying the same pi1 we've been looking at all this time. In genus 5, in not genus 5, but 5 marked points, it's going to be the same. Here I have 5 marked points, so 1, 2, 3, 4, 5. And up to diffeomorphism, it only matters what points are surrounded by the loops I take. A generating set of Dane twists. Of course, there are loads of Dane twists, but I don't need them all to generate. There are far too many. A generating set of Dane twists is given by these 4, and then I need a one that's, so I've got 1, 2, 2, 3, 4, 4, 5, and then I need one surrounding 5 and 1. So these loops are called x12, x23, x34, x45, x51. They satisfy a bunch of relations that I'm not going to write down. And they generate the group gamma 05, which is the diffeomorphisms of mod diff 0, like I said before, which is pi1 of M05. Okay? Now, the choice of what? Oh, yeah. No. Sorry, rubbish. Let me make a better picture. No, of course. I need something surrounding 1, 2, something surrounding 1, 3, 2, 3, something surrounding 1, 3. 1, 2. And so x equals x1, 2, y equals x2, 3, and z equals x1, 3. Yeah, sorry. And here it's the same. The 1, 2, 2, 3, 4, 4, 5, and then I need my 5, 1. Okay. I just want to quickly go back to my very first thing that I said in my very first lecture, which was that Lie algebra, where I said you have a third relation on the Drinfeld associator with x1, 2, 2, 3, 4, 4, 5, 5, 1, but I'm not going to say what they are. But now I can say what they are, because this is a group with these generators, and that was the Lie algebra associated to this group. So of course, if I had more time, then I could give you all the generators and relations. We could even calculate that Lie algebra exactly, which I don't have time to do, but this is the definition. And the xij's in that just came from taking the Lie algebra associated to this group. Okay, now I think I'm ready to give you the definition of GT. And you will recognize it because it's the same definition as the definition of that Lie algebra, except that now it's a profinite group. So it's a profinite group consisting of these pairs lambda f in z hat star cross f2 hat prime. And I take only those that satisfy 3 relations. Before I write down the other 2 relations, I'm going to just explain the notation quickly. Back when I had a Lie algebra, I said I take an element of Lie xy and I apply it to yx or other variables, and that was fine, because it was just a polynomial in x and y. But now an element is, f is an element of this, and you might say, but that's weird. What do you mean when you apply it to x and y or to yx or something? So I really should explain what I mean. So here's my notation. Anytime I have a homomorphism of f2 hat to some profinite group, finite, profinite, whatever, and here I have my f, and let's say my homomorphism is defined by sending my generators xy to 2 generators to 2 elements a and b. Well, I write this notation for the image. It's just a convenient notation. What this means is the image of F under such a homomorphism. So now that I've defined this notation, I can write F of thing, thing. And that's now well defined as a notion. So here M is just lambda minus 1 over 2. And now the 5-cycle relation. Okay, so I don't have to tell you that the xij's are all in the pro-finite completion of the group I just defined. So it's what this is 5 different images of the same F under 5 different homomorphisms of F2 into gamma 0, 5. Okay, notice that curiously, whereas when I was in the Lie algebra, everything was abelian, so I could add them up in the cyclic order. Here, and this is important, it actually advances by 2 each time, and it's really a very different relation from if they advance by 1 each time. There's a good reason for that. So, for lack of time, I'm going to change my plan and give you all the statements, as many as I can of the main statements first, and then I'm going to see which ones I can prove. Yes. Thank you, Makoto. What would I do without you? So this is a very, very interesting question for those who like open questions. We have, like I said before, you take any pair lambda F like this, like I said in a previous lecture, and you apply it to F2 hat by doing this. And it gives an endomorphism, and therefore you can compose them, and that makes a monoid. But here, I want a group, not a monoid. So what I'm going to do is, I'm actually only going to take pairs such that this is an automorphism and not an endomorphism. Okay? So the fact is, it's not a known thing that it may work for all lambda F. We just don't know. It's possible that all lambda F always induces something which is invertible. But we don't know. So for the time being, we're really obliged to, indeed, to add this. Now I'm going to write one more relation. And for this one, I'm going to need to draw a picture. So let me call this GT sub G for a reason that I'll tell you pretty soon. So it's equal to lambda F in GT satisfying a further relation. So this further relation, I'll write it down first, and then I'll define all the terms that occur in it. I'm writing it down, although it's a bit complicated, because I think it's important to see that it's a small, finite relation that lives in a place that we can easily look at. Okay. Especially with all the indices here. Okay, now when you look at this relation, your reaction is supposed to be how beautiful and not how awful, which is what it might be. I didn't tell you that it wasn't supposed to be that. Because really, this relation reflects astonishingly beautiful geometry of the moduli spaces. So let me define all the terms that appear in that thing, and then I will state all the nice theorems, and then we'll see how far I can get with the proofs. Okay, so here, all the letters occurring here, E1, E2, E3, A1, A2, A3, these 6 letters are Dane twists on the topological surface sigma 1, 2. So it's a genus 1 and it's got 2 marked points on it. I'm going to draw it twice. So I want to tell you, so the relation lives inside the group gamma 1, 2, which is the diffs of this sigma 1, 2 mod the diff 0. That is where this relation lives. It lives inside this group with a profinite, of course. So in order to tell you who the Dane twists are, all I have to do is tell you who the simple closed loops are that they're along. So here they are. If I had different color chalk, it would be great. Is there? No? Actually, yeah, there's a subtle difference, but I think they can be points here, no? Please don't make me get into that. Okay. So these are A1, A2, A3. These are 3 Dane twists along the 3 loops that I've drawn. And E1 is this loop. E3 is this loop. So E1, E3. E2 is this loop. And the last little thing I have to tell you is who row 2 is. But for that you have to, I'm going to tell you why this is later. Believe what I'm going to say for the moment. I hope I'll get to a proof of it. There is a unique G in F2 hat such that f of xy equals g of yx inverse g of xy. Okay, this is very important. So believe it temporarily. I really hope I'm going to be able to get back to it. And if you look at what this means in the abelianization of F2, remember this becomes 1 in the abelianization. So what that means is that gxy in the abelianization, it has to be xy to some power, which is row 2. That is, x and y have got to be to the same power. And the row 2 which appears is the row 2 associated to little f in this way. So that's the row 2 that appears in that relation. Okay, so that gives us a definition of that relation. Now, the whole point of this is 3 theorems. So theorem 1, GQ injects into GT. This is really the whole point. So I'm going to spend time on giving you a sketch of like at least 3 different proofs of this result. The whole point is that's why this group is interesting, because we know that GQ, you can see the elements as pairs, lambda f. So what I'm saying here means that those pairs satisfy relations 1, 2, and 3. In fact, we could do this. We could do better. Okay? So what that means is that the 3 conditions and plus the additional condition are necessary conditions on the F sigmas. Okay, but so I pulled out 4 necessary conditions on the F sigma. So what? So maybe there's a trillion million more. Why are these 4 important? So that's what theorem 2 is about. GT is the automorphism group of the category C pi for C equals the category of all genus 0 moduli spaces. Now this is already very important because, wow, before when I showed you that we took the category of all Q varieties and then we got GQ, there were way too many pi ones to make any computation about what the automorphism group could be. Here I'm still taking an infinite number because I'm taking the m0n's for all n greater than or equal to 4. Yet we only have 3 little relations and that suffices to describe the whole automorphism group. And as a matter of fact, and this is also very important, this is something that was predicted by Grothendieck. It's enough just to take these 2. I'm not talking about the morphisms between them, okay? I'm going to say more about that later. There are Q morphisms. There's a whole family of Q morphisms you have to take in this category, which I'm going to describe more explicitly later on. This thing here, this theorem, this result, this is called the 2-level principle. What Grothendieck said is, the wonderful thing about studying moduli spaces is that moduli spaces are all built up from the ones in dimension 1 and 2. So really, you're never going to get anything new after you've looked at dimensions 1 and 2. And that's exactly what this result says, because the dimension of this, the complex dimension of MGN is 3g minus 3 plus n. So what we've got here is a dimension 1 and a dimension 2, and so it totally corresponds to what he called the two-level principle. Theorem 3, GTG, well, of course, you can practically predict what I'm going to say. It's just what happens when C is now all moduli spaces. And in fact, it again suffices to take only M04 and M05. And in higher genus, you've got only one of dimension 1, it's M11, which is genus 1 with one mark point, that's elliptic curves, the moduli space of elliptic curves. And then you need M12. Now, M11 is very, very similar to M04. M04 is P1 minus 3 points, as we saw, and M11 is just a quotient of that by the action of S3. So, in fact, although when we wrote down GT, we said these two live in M04, F2, and that lives in M05. But a better way to look at it is that one of these actually lives in M11, and one lives in M04, and this lives in M05, and this lives in M12. We've got four relations. We've got one in each of the four main spaces. And the whole theorem is that we can now take all moduli spaces. Firstly, we don't get anything more. We've computed the group, so we know it. Secondly, we now have all moduli spaces, and in a sense that's very heuristic and very visionary, and nobody knows how to make concrete. This should be, quote unquote, enough to capture everything that happens with all varieties all the time. Because just think of dimension 1 for a minute. So dimension 1, what is it? Varieties of dimension 1, they're curves. They're all in the moduli spaces. They're all there. What about dimension 2? Dimension 2 things are surfaces. Dimension 2 complex surfaces. Surfaces can always be realized as fibrations over something of dimension 1. And in fact, when you take a moduli space and you do the operation of taking every point in there, which is a Riemann surface, and erasing the last point, what you get is a thing like this. You get a map down, which is a fibration. And every surface realized as a fibration over a curve fits into a moduli space cover here, maps in. So I've already kind of justified that everything that goes on with surfaces and curves lives inside the moduli spaces, and you can go on and make the same reasoning for all cube varieties. This is not a good explanation. This is not math. This is hand-waving. But it's supposed to give an idea of why Grothendieck might say, just look at the moduli spaces, look at the pi1 of moduli spaces. So if we to believe that looking at the moduli spaces is enough, is equivalent, gives you everything that you get by looking at all Q varieties, and since we know that when you look at all Q varieties you get GQ, we could daringly conjecture, ask, I like the word ask better than conjecture, because conjecture means you're kind of sure, which isn't the case here. If GQ is equal to GT, I'm going to put a G here. But frankly, we don't know that GTG is different from GT. This is not known either. This is clearly in. But for all we know, it's equal. I mean, we have a new relation, but nobody's proved that this new relation is truly independent. Personally, I believe that it's independent of the other three because of the appearance of the M12, but that's not a proof. Okay? So this is the goal. That we've gotten necessary conditions. We know that those necessary conditions really describe everything that comes from the geometry of all the moduli spaces. And we have some heuristic visionary reasons to ask if those necessary conditions might be sufficient. So that's kind of a picture of Grothendieck-Teichmüller theory.
I didn't hear what you were saying earlier about dimensions. You said somehow it's sufficient to consider dimension 1 and dimension 2.
Yeah.
What was the reason, the heuristic behind it?
Well, it is because a surface can always be built up by cutting it into it. Well, actually, I'm going to explain it at length. But the idea is if you put a lot of simple closed loops on a surface, you cut it into small pieces. And then analogously, you have maps from moduli spaces into each other corresponding to this. And in this way, by these maps, you build up all the moduli spaces from the small ones. Another rough way to say it is somehow that the dimension 1 ones kind of provide generators, the dimension 2 one kind of provide relations.
The senior, more elementary question was, did you explain already how GT had maps on C pi?
No, but I will. Oh, it's au choix. It doesn't matter. M11 and M04 are practically the same, so you can consider either or both of these as coming from N11. I'll actually explain that also. You could drop it. Yeah, no, I like to keep it because it's prettier to have one of each. But the fact is, it's very natural to consider both of these as coming from N11 also. I'm going to pretty much explain that as well as I can. So now I've got loads of stuff to prove, and 5 minutes. So what I'm going to do is I'm going to just give a sketch of a proof of theorem 1 and leave the rest for next time. I'm going to give 3 sketches of proofs of theorem 1. The first one, it's not a sketch of a proof. I'm going to state a theorem, which immediately implies theorem 1. This theorem is quite pretty. So take the outer automorphism group of gamma 0 n hat for n greater than 4. Okay? Now, there's a very natural subgroup living in here, Sn, the permutation group. How does that give outer automorphisms of gamma 0 n? If you think about it, it's very easy. Sn permutes the endpoints. And this induces an action on the Dane twists, an outer action on the Dane twists. You have to think about it a bit, but it's really not hard. Induces an outer aught of gamma 0 n by xij, that generator xij goes to x sigma I sigma j. Okay, why does this give an outer automorphism? You know, why does it respect the relations? Or stuff that you have to verify, but it's easy to verify. And the theorem says, that's not the theorem. That's a preliminary facts to the theorem. So suppose that I look at all outer automorphisms of this group which commute with Sn. One thing I know is that these outer automorphisms, Sn, you can also realize it is it's equal actually to the automorphisms of the moduli space itself. Just by, again, it takes the Riemann surface, it permutes the point, that gives me another Riemann surface. So each point's a map to a point, it's an automorphism. And those are just permutations, so as maps from one Riemann surface to another, they define over Q. So it commutes with GQ. So we saw that GQ lives inside this outer automorphism group. We saw that several times, the fundamental exact sequence that Makoto talked about for every variety. And GQ, for the reason I just said, commutes with Sn. So GQ is in here. But the theorem says this, that GT is exactly the automorphisms of gamma 0 n that commute with Sn. Okay, so that's a hard theorem with a bit of a long proof, but it has the advantage that it proves theorem 1 as a corollary. So that's one way of seeing it. I guess I won't have time to give you all 3, so I'm going to give you one more. This one is really cute. We take...
Could I just repeat a little bit of the previous question? In this case, it is easy to see how GT hat acts on gamma 0 n.
It is. It's really easy. But I really, really would rather leave it till next time. It's just one formula, and I'm going to get there in order. I'm going to write down the explicit formula. It's really a simple formula. But I want to say this. Okay. So what Makoto said this morning is that now if I take the pi1 groupoid here, or maybe it was Dick who said, I can't remember who said, but anyway, we saw what a groupoid was, and this is a path in the fundamental groupoid, and GQ acts on those. Anytime a path on P1 minus 3 points or anywhere else goes from a Q point to a Q point, GQ will map it to another path from the same point to the same point. And what he said was if P is like the most important path in the world, then sigma P equals P F sigma. We saw that in Makoto's talk. But what I say is, well, since it always acts, then sigma also acts on R, which is the path from here to 1/2. And it's going to go to R times from G sigma. And now what I've got is, let theta of Z equal 1 minus Z. Well, R theta of R inverse equals P. Now I apply sigma to both sides of this. Sigma commutes with theta because this is defined over Z. So what I'm going to get is RG sigma inverse RG sigma is going to equal PF sigma. And if I push the paths together, all I get is theta of G sigma inverse G sigma equals F sigma, which is the same as saying G sigma of yx, because theta switches y and x, inverse G sigma equals F sigma. And let me put xy here. Okay, so this is the thing that I wrote before that I promised to explain. Here I've only explained it for GQ. Before I stated it for all GT. It is true for all GT. Okay, but look, this totally explains why F sigma satisfies relation 1. Because relation 1 says F sigma xy, F sigma yx equals 1. And that's now trivial, completely trivial. You just apply it to this and they cancel out and it's 1. So this proves relation 1 in this very simple way, just by cutting P into two parts. And you can prove relation 2 and 3 the same way. For 1, you have to cut P into a weird path that goes up to a third root of unity, come down. And for the third one, you have to go into a higher moduli space and do it, but it's exactly the same technique. So this is another way of proving that the F sigmas coming from GQ satisfy 1, 2, and 3. Okay, well, I've given you 2 proofs of theorem 1. That's already something. But I will talk about what you said starting next time.